Okay, now we are working on target 4-3. We have a little bit more to do on that. I've left the easier things to the end. You've done the bulk of the hard stuff. So we've talked about naming ionic compounds. You've done a bunch of stuff on that. Our lab was about that. We haven't talked about covalent compounds. And they have names too. But there's no one naming system for these things. There are an enormous variety of covalent compounds. All of them have slightly different naming rules. So yeah, we could literally spend a year talking about that, and there is a class for that. It's called organic chemistry. Maybe someday you will get to the privilege of taking that. But we aren't going to do that. I'm going to pick just some categories and teach you the rules for those. Those categories are relevant to what we're doing in the future. All right, so we're talking about covalent names. All right, so when it comes to covalent names, as I had said, there are different systems for different families of covalent compounds, but they do all have one thing in common. Covalent names use prefixes. Okay, so for example, two of the most famous compounds in the world, all right? Carbon dioxide, dihydrogen monoxide. They have something in their names that ionic compounds do not, and that is prefixes. There are no prefixes in ionic compounds as a rule. So I'm talking about that, and that, and that. So, dang, got something. Do I have food on my face? I apologize, but got something. Now, okay, yeah. Now, the reason why there are prefixes is because there's no charges. There's no ionic charges in these compounds, and therefore you can't use charge equivalents. Now you could move dots in many cases, but that gets really cumbersome and doesn't always work. So, in other words, would be no way for you to know the ratio if I just said carbon oxide. I have to tell you in the name how many. Otherwise it would be very difficult for you to know. So, in a covalent name, what you are doing is just translating the name from left to right. All right, carbon, it's a prefix, not a suffix. Because it's a prefix, it's attached to the oxide, correct? All right, it's good to know. So that would mean carbon oxide means O. And IDE is thrown in as a suffix, just so you know we're talking about a compound. All right, same thing with this, dihydrogen monoxide. Okay, these are prefixes. They're attached to, they come before the element that they mean, so you would just translate the name. Well, let's see, hydrogen, I got two of them, and one oxygen. There you go. That's what it takes to take the name of a covalent compound and write the formula. It's just translating the prefixes. At this point in time, I would love to tell you that all the prefixes are the universal, but they're not. Different families of covalent compounds use different prefixes, and so you end up with this mess of prefixes. So I'm going to try to make that mess a little bit narrower for you. All right. I want to talk about a very famous, well-known family of covalent compounds. They're called the hydrocarbons. And here's how the hydrocarbons work. This is carbon. Carbon has 4 valence electrons. I could do the 1s2, so it's 1s2, 2s2, 2p2. All right, so it's got 4. So its Lewis dot diagram would look like that. But just for teaching purposes, permit me please to move this dot up to there. Just it'll help make some sense of what I'm going to draw here. The neat thing about carbon is because it has these 4 valence electrons, it's able to form covalent bonds with itself. So another carbon right here, they could form a shared pair. Because remember, a covalent bond is between a shared pair. So we have a pair of electrons here. They could pair up. Now these 2 electrons belong to both carbons. And if I have another carbon here, I can chain that one up. These 2 could have a shared pair. And I just keep going and going and going. And the neat thing about carbon is you can make these chains incredibly long because it's a pretty flexible material. It's not the only atom that has 4 valence electrons. Silicon, germanium, tin, and lead will. But as far as I know, germanium, tin, and lead don't chain up like this. Silicon will, but the chains are brittle and they break after a certain length. So carbon has this property of chaining up and remaining flexible, so you can make some really long chains. What's a really long chain? Several million of these things stuck together. We're not going to go that big, all right? So, all right. A hydrocarbon is when you take a chain of carbons, and notice you have single electrons here. You fill those other electron spaces with hydrogen atoms. See, they could have a shared pair there. And you could have a shared pair here. And a shared pair here. Now, this carbon has 8 electrons through sharing. It had to form 4 shared pairs. It's happy. It's got its octet. Each hydrogen has 2, and that's what hydrogen gets, 2. That's as far, remember hydrogen and helium are on the first main energy level. They can't have 8. They get full after 2. It's called a duet, not an octet. So the hydrogens are happy. Hydrogens have full outer shell, as small as that shell is, and this carbon has a full outer shell, all by sharing. So each atom has what they want. All right. So all of these open electrons here can pair up with hydrogen, and you have a compound that's made of a carbon chain in the middle surrounded by hydrogens, and we call it a hydrocarbon. hydrocarbon. I wonder what elements are in that. Hydrogen and carbon. People will think it's water and carbon because hydro can also mean water. That's not what it means in this case. All right, so that's a hydrocarbon. Hydrocarbons are very useful compounds. Hydrocarbons are petroleum products, oil, gasoline, things like that. Those are all hydrocarbons, which are pretty dang useful. So that's why I'm teaching you these. We are going to see these pop up in the future in other units, and it's very helpful to me that you know what a hydrocarbon is. Okay, so now we have a problem. The problem is that there's so many dots. The dots can become confusing rather than helpful. So what happens in hydrocarbon compounds is, I mean, we can teach it this way, but once you have seen it, we will replace the dots with a line. And the line does bring a certain amount of clarity, where the line, each line here represents a shared pair. There's too many dots. You get just too many. And so we get lines instead. When you draw these lines and you show every atom and how it's bonded to every other atom, this is called a structural formula. Structural formulas are the norm with hydrocarbons. Notice when we did the ionic compounds, we didn't care where the ions were in relationship to the other ions. All we cared about was the ratio of the ions. Ionic formulas are not structural. But the tradition is, with hydrocarbons, to show structure. So, structural formula. Yeah.
Does those lines today only show two?
I couldn't hear what you're saying.
Does it only show 2 dots lines?
Yeah, 2 dots per line. Okay, so that's great, Mr. Yan. How do you name them? All right. Because the formula, the target says, you need to evaluate the name and build the formula. Let's talk about the names. Okay, so the naming system I'm about to show you is not related to these two. The only thing that would be in common is there are prefixes. That's it. And the prefixes are different too. Hydrocarbons have their own set of prefixes. I do not necessarily know where a lot of these prefixes came from. It does seem like some of them are Latin, some of them might be Greek. I don't know. Nor did I make this up. So you turn in your survival guide, and you should be able to find the list. I see Gavin's got them there. All right. Of at least the first 10. Pretty much after 10, we don't do prefixes anymore. We just say the number, 11 this and 12 that, and so forth. For smaller hydrocarbons, we use prefixes, and the prefixes you can see there. Meth equals 1. Where meth comes from, I don't know. I just know that that is the hydrocarbon word for 1 carbon. And then F is 2, prop, not prop, prop is 3, and then bute, not but, all right, 4. After that, it kind of makes sense because pent is 5, pentagon, pentagram, all right. Hex might be new, and hex is 6. Hept is 7. I mean, you're going back to your geometry days. Remember your geometry problems? You have a regular heptagon. Determine the surface area of the heptagon, or whatever. You know, you're like, oh, what's the formula for the? How does the? I just last year my daughter took geometry. I remember helping her a little bit with like some of these problems. But anyway, you might remember that the last time you used the word hept. Oct. Everybody gets oct. Okay, that's 8. Non is 9. Dec is 10. And yes, there are those kids that I'm just, maybe there will be this one this year that's like, is that why a decade has 10 years? Yes, that's why. Okay, yes, that is exactly what. All right, dec means 10. Now, so here's how you name hydrocarbons. That's how you use the prefixes. The way a hydrocarbon name works is the first thing you name is the number of carbons. This is called a carbon backbone. The carbon chain is in the middle and the hydrogen's around the outer edge. So that's called a carbon backbone. The first thing you do in the name is you name the carbon backbone. So how you do that is that's what the prefix is for. This right here would be prop. Then, if the molecule, if the structure, hold on, I used that word molecule, I try to avoid using that for now. If this structure is a hydrocarbon, we put a last name on it. Prop means it's a hydrocarbon that has 3 carbons in its backbone. Ane means it's a hydrocarbon. So propane. All right, so hydrocarbon names are one word. They will contain a prefix. That prefix is telling you how many carbons are in the backbone. Ane is just reminding you that it's a hydrocarbon. That's all you're doing. You don't say the word hydro or hydrogen. You don't say the word carbon because you're already in the context of a hydrocarbon. You don't need to say hydrocarbon every time. All right. So all you're doing in a hydrocarbon name is you are telling me how many carbons are in the backbone and sticking ane on the end of it just to remind us that it's hydrocarbon. Okay. So what you would do is this.
Actually, that bottle of propane, is that actually
What?
propane?
That's the actual that's the actual structure of a little propane floating around.
Propane.
Okay, so at least in 2 dimensions. Now, the target says I can write a compound's formula and determine its percentage composition by evaluating its name. So if I give you the name propane, you would sit there and go, that's a hydrocarbon. I know that because it's an ane. All right, and then prop is telling me how many carbons are in the chain. So you would come up and you would give me a structural formula. You would say, okay, here's the carbons. Notice each carbon has 4 bonds because it has 4 valence electrons. So I got my carbon backbone there. Then I'm going to put hydrogens on each one. That's propane. And that's it. That's what the Chromebook. Griffin. Now, yes.
So every hydrocarbon ends with ane?
Yep. So, all right. Now, let's say you have a test and you are asked to build a structure for a hydrocarbon. All right? You know the prefix is the number of carbons in the hydrocarbon. Which prefix on there would have this be the lowest number? What's the smallest hydrocarbon? Meth. Okay, so yeah, let's say you had methane. That's the name, and you were asked to build a formula. And you were like, oh wow, I got lucky. That poor kid who got decade is gonna be there for a while, all right? So what I would do is I would translate Methane tells me it's a hydrocarbon. It says ane, it's a hydrocarbon. So I know that what I'm doing is writing the carbon backbone with a line for every electron that will get paired up. And then I pair them up with hydrogen. That's as hard as hydrocarbons are. Yeah.
Do we have a list of like the numbers, or do we have to memorize?
You have to memorize them.
Let's go to test.
What?
Let's go to test.
It's a target. Yep.
Like physics. Like, you'll give us a word and we have to like.
Yep.
Oh, great.
So now, speaking of that, because I missed last Friday, and so therefore I'm kind of a day behind. I will not have you do a percentage composition of a covalent compound. Percentage compositions will be left for ionic compounds only. So to do a percentage composition of this, you would say I've got 1 carbon, 4 hydrogens. I add up all the masses and then divide, but I'll restrict it to ionic compounds. Now, okay. One more family. One more family. So you will have the ionic compounds, you'll have hydrocarbons. I do want you to know these two, which aren't in a family, they're just kind of random, all right, but be able to translate those. But the last family, we're trying to talk about alcohols. Alcohols are a family of carbon compounds. They are related to hydrocarbons. What an alcohol is when one of the hydrogens on a hydrocarbon, yeah, don't want it anymore, and nobody else is going to leave to go to the bathroom either. So, one of the hydrogens has been replaced with an OH group. That's it. So just one of them. Now, you don't necessarily know which hydrogen has been replaced with an OH group, so we just by tradition, it's just this far right-hand one. It could have actually been any of them, but this is not a hydrocarbon because it has an oxygen sitting there. Thus, not a hydrocarbon. This is an alcohol. You take a hydrocarbon, clip off one of the hydrogens and stick an OH on there, you now have a different compound slightly, and we call that family alcohols. So how does this affect the name? Well, the prefix does not change because alcohols are just modified hydrocarbons. The prefix stays the same. This is still a meth because it has 1 carbon. But this part changes though. It's not an ane, this is not a hydrocarbon anymore. So an alcohol's name will end in A-N-O-L, or anol. So this is methanol. And that anol tells you you're dealing with an alcohol, and to take the hydrocarbon, clip off one of the H's and stick an OH on there. Alcohols are industrially very valuable chemicals. They range everything from solvents to fuels. And so going into the future of the class, you are going to be running into, especially the second semester, you're going to be running into alcohols as fuels, hydrocarbons as fuels, and we use these things for other things as well. So if you know the ionic compounds, you know those two kind of oddball ones up there, and then you know the hydrocarbons and the alcohols, you're good. You've got most of the bases covered for the future of our future discussions. All right, so here's what would happen. You know, let's say that it's next week, and you have okay. You're given the name pentane, and let's say you're given the name hexanol. All right, so you discuss, build structures for these based on what you know, and we'll check them out.
Is it just one OH for alcohol?
Correct, just any hydrogen you want, but I'm always going to take that far right one and clip it off. Usually, the covalent compounds are stress relief. Kids usually can get this. You only have to memorize 4 prefixes, meth, eth, prop, and bute, because all the other ones make sense with your life experience. Step 1, how many are in a pent? 5. Okay, so I'm going to go 1, 2, 3, 4, 5. Then I'm going to connect all these with a shared pair. Done. And then I have shared pairs that are going to come out here. How many lines should there be on a carbon? 4. This carbon has 4 valence electrons. So this carbon has 4, but it's sharing one of these with the other, so this one would have 4. So they all have 4. Then pentane. All right. So now I want to draw a hexanol. I can just modify the pentane. If I wanted to convert this formula into a hexanol, what would I need to do? Okay, if I get rid of a hydrogen and add an H, I now have a pentanol. Like this? So now I just made a hexane. Yes, hexanol. There you go. Okay, so all right, so I can write a compound's formula and determine its percentage composition by evaluating its name. So you've got the full lesson here. The bulk of the work goes with the ionic compounds because you got to do charge equivalents, complex ions, transition metals. There's a bunch of stuff there. Okay, so with that being said, let's wrap this up. Okay, so we're going to kind of come full circle here. flip to target 4-4. Okay, so what I've got here are two crystals. So this one, the crystals are, I think they're hexagons, they're just small. And this is calcium carbonate, which is an ionic compound. This is copper chloride, I think, which is an ionic compound. My point is that ionic compounds form crystals. Covalent compounds can form crystals, but they don't have to. But ionic compounds will form crystals. And it's easy to see why if you study sodium chloride. Sodium chloride is a sodium atom stuck to a chloride atom. This is positive, this is negative. And just because those are stuck together does not mean those charges go away. It just means mathematically there's one negative for one positive. They just don't disappear. So, if you have another sodium chloride that formed near this one, and they get near one another, this could snap magnetically to this one, and this could snap magnetically to that one. And two sodium chlorides will stick together, in other words, because the magnetic charges don't go away. They're just mathematically equal in terms of their quantity. And if this were to keep happening over and over and over again with sodium chloride units, what you will build is you'll have a sodium here, and a chlorine here, and a sodium here, and a chlorine here. And so these are sticking to each other, alternating, positive, negative, positive, negative, positive, negative. But it can go this way as well. Negative, positive, negative, positive, negative, positive, positive, negative, positive, negative, positive, negative, and just keep going. All right, so here's Cl, here's an Na, Cl, here's an Na, Cl, and here's an Na, and it can go in 3 dimensions. So you can stack, there could be a chlorine here, and then a sodium, and a chlorine and a sodium, and chlorine and sodium. And so if this kept getting bigger and bigger and bigger and bigger and bigger, what shape is this going to make? A cube. And when you look at sodium chloride crystals that are mined out of the ground, they are in fact cubes. This is under a microscope. This is probably taken out of a salt shaker. They don't pour those into molds and bust them out like ice cubes. They come naturally this way, out of the ground. If you grind them up, they will fall into these small cube shapes. That's because sodium chloride stacks in this way and will just keep getting bigger and bigger and bigger until it turns into a huge cube. So, more complex ions, like things that have 2 to 3 ratios and 3 to 1 ratios or 2 to 1 ratios will stack in odd ways and will often lead to a beautiful geometric shape if it gets big enough. I just can't draw that. So you need supercomputers to figure some of this stuff out. So, but it's easy to see on a sodium chloride. And there's no set size limit to this. The size of the cube is dependent on how many sodiums and chlorides you have. So you could have a tiny cube, you could have a cube the size of a mountain. All right. Yeah.
What about a diamond?
Not an ionic compound. So, now, therefore, here's how we're ending the unit. What is an ionic formula representing? It cannot represent the entire group because there's no size limit on the group. You could have a huge cube or a tiny cube. What an ionic compound's formula represents is just the most basic repeating unit. Mathematically, the most basic repeating unit. And on this, what is the most basic repeating unit?
Sodium
The
chloride.
NaCl on a 1-to-1 ratio. So an ionic formula is just representing the size, just that most basic. It has nothing to do with the size of the object. But covalent compounds do not do this. When you drew a pentane or you drew that hexanol, you are actually representing the complete size of that group of atoms. They don't stick together with negative and positive because there aren't any negatives and positives. So a covalent compound is describing a discrete unit. And we call that unit a molecule. A molecule is a discrete unit of covalently bonded atoms. Ionic compounds do not form molecules. They form crystals. And the formula is just the most basic mathematical ratio in the crystal. So, therefore, we would not ever refer to an ionic compound's formula as a molecule. A molecule of sodium chloride, that makes no sense because that's an ionic compound. A molecule of methane does make sense. All right, so we would refer to ionic compounds as formulas only and molecules for covalent compounds. So, all right, in a covalent compound, you make a molecular structural formula showing bonds and atoms. In an ionic compound, you show a ratio only. All right, so the formulas look the same, but are communicating different things. All right, and thus this unit is over. So now, what we'll do on Monday is we will review, we'll go over the exam description, talk about the essay, okay, I guess that's what it is. Yay.